Swayam Prabha. Digital India. Educated India.
So, welcome to the 15th lecture of Cryogenic Engineering under the NPTEL program. In the earlier lectures on gas liquefaction, we have talked about various cycles and I will just go in brief about those cycles. We have seen an ideal thermodynamic cycle in which all the gas that is getting compressed is getting liquefied. So, whatever gas ideally in the ideal cycle, whatever gas gets compressed, it gets liquefied 100%. Then we came from this ideal cycle to a little practical cycle, which was a Linde-Hampson system. So, in a Linde-Hampson system, a heat exchanger is added to the thermodynamic cycle and so whatever cooling effect is produced, the cold is conserved. So, a heat exchanger is used to conserve the cold and only a part of the gas that is compressed is liquefied. So, in first case all the 100% gas which was compressed got liquefied, here only a part of the gas that was compressed got liquefied. Then we went for the second modification, which is a pre-cooled Linde-Hampson system. It is an independent refrigerating system is used to pre-cool the gas before it enters the heat exchanger. The mass ratio of this refrigeration cycle corresponding to the maximum yield is called limiting value, meaning which that one cannot go on increasing the refrigerant flow in the auxiliary cycle, because after a particular R value, addition of that R value, there is no significant effect or there is no effect on the yield, and therefore, this is a limiting value of the R or the amount of refrigerant that is flowing through the auxiliary refrigeration system. We have seen this system in detail in the earlier lecture. Then we went for a Linde dual pressure system, wherein we used two compressors. The Linde dual pressure system is a modification of simple Linde-Hampson system in order to reduce the work requirement. In this system, the work requirement per mass of gas liquefied decreases when the compression of the fluid is done in two stages and for different mass flow rates. I think this is very straightforward and this is what we did during the last lecture. So, we had two compressors over there and both the compressors had different flow rates. As part of the gas which was compressed in the first was the second stream joins there and the total amount M is getting compressed only in the second compressor, while the first compressor had less amount to compress. Now, going ahead from there, we come to a different cycle now. And the outline of this lecture which I am going to talk about is again continuing on the same topic, gas liquefaction and refrigeration system. What I am going to talk today about is Claude cycle or sometimes called as Claude cycle. I will call it Claude cycle. Now, Claude was in 1920, Claude developed an air liquefaction system which is famously known as Air Liquide today, a French company. And during my first lecture, when I talk about the chronological event that in the field of cryogenic engineering, Claude figured in that list also. This is a very big company as of now, which makes helium liquefier, nitrogen liquefiers. Under this Claude system, I am going to talk about the expressions for liquid yield, the work requirement and also the parametric study, which is a very important constituent of the Claude cycle. So, introduction to the Claude cycle. In order to achieve a better performance and to approach ideality, the expansion process should be a reversible process. Till now what you have was a Joule-Thomson expansion, which is an irreversible process. In the earlier lecture, we have seen that a JT expansion or a Joule-Thomson expansion is an irreversible isenthalpic expansion, and expansion using an expansion engine is an reversible isentropy process. We have talked about this earlier in one of the earlier lectures, that expansion could be achieved by an isenthalpic expansion or an isentropic expansion. In a domestic refrigerator, for example, what we have is a Joule-Thomson expansion achieved using a capillary tube. Till now, whenever we have expanded the gas, in the earlier cycle, we have found that a JT expansion is used, which is an isenthalpic expansion and it is an irreversible process, and therefore, we have to worry about the inversion temperature of this gas, below which only when the JT expansion is carried out would result in cooling. Now, in this Claude cycle, we will talk about an expansion engine where you got a piston and cylinder kind of an arrangement, where the work also is done by the system in an expansion engine And in this case, when the expansion is carried out using such an engine, the process is a reversible isentropic process ideally. Ideally, it will be a reversible isentropic process, and this would always result in cooling, and one would not have to worry about the inversion temperature of the gas. So, for any gas, an isentropic expansion results in lower temperature irrespective of its inversion temperature, that is TINV. So, this is clear now that isentropic expansion is always preferred and is always basically result in lowering of temperature, which is not so in case of a JT expansion. So, this is a schematic of a Claude cycle, and what you can see from here, it has got a compressor over here and it has got an expander over here, and we got a heat exchangers 1, 2 and 3, and there is a JT valve at the end where the liquid is yielded in the container at this point here. So, the schematic of the Claude cycle is as shown here. It consists of a compressor, which is this, and a 2 fluid heat exchangers. So, there are 3 heat exchangers 1, 2 and 3, and there are 2 fluids. As in earlier cases, we have found that there were 3 fluid heat exchangers also, and a JT expansion device and a makeup gas connection. So, after getting the liquid at this point, the gas would go back, and whatever amount m dot f as you get at this point in time point here, the makeup gas is added equal to m dot f at this point. The system has an expansion engine operating across the second heat exchanger as shown over here. So, what you can see from here is when the gas is getting compressed, it goes through the heat exchanger, and a part of the gas, that is Me, is taken off from here. The gas is expanded to the expansion engine over here, which produces cold, and this gas, the cold gas at the end of the expansion, joins the return stream. The return stream is coming basically from the gas which has not got liquefied at this point. The whatever amount of gas is coming from 6, of which only m dot f gets liquefied, and the return stream will have the remaining gas. This gets joined to m dot e, which is coming from expansion engine, and the whole gas goes back and gets compressed with a makeup gas connection at this point. So, in this system, the energy content of the gas is removed by allowing it to do some work in an expansion engine. So, what you get at the end of the expansion over here is WE, which is the expansion work, that is the work done by the expansion engine. So, here on the compressor we are doing the work, while at this point here during expansion we get WE as the work done by the system. As shown in the figure, a part of the main stream of gas is expanded from 3 to E. So, a part of the gas which is Me is taken from this M gas which is compressed, and this expands from point 3 to point E, where it joins the return stream. And this is the stream which is going to produce cold, so that you go near the dome, and then we have a JT expansion resulting in getting liquid at this point. This process of expansion is a reversible adiabatic expansion. That is what we are talking about, ideal expansion in this case. However, it will have its own efficiency, and therefore, it will not be a clearly 100% isentropic expansion, but as of now we will take it as 100% expansion, and we will worry about the irreversibilities later. So, if I plot this cycle, the Claude cycle, on a temperature entropy diagram, let us try to understand this. The 1 to 2 process is a compression, which is what you can see here. 1 to 2 process is the isothermal compression process. In the heat exchanger number 1, this m dot is cooled by the return stream from point 2 to point 3, and you can see from point 2 to point 3, and this temperature matches with the return stream at this point, which is 9 over here, assuming that this heat exchanger is a 100% efficient heat exchanger. Now, at this point, now from where the gas is expanded is a very important question in case of Claude cycle. So, why should I expand the gas from only 3? Okay, why not it should be at still lower temperature and things like that. That has to be worried, and the effect of this point 3 we can understand in the subsequent slides. So, the gas is taken off from this main circuit at point 3, and it is expanded isentropically from 3 to E, and this you can see on the TS diagram, that the gas is taken from high pressure line at point 3 and is expanded from point 3 to point E. So, what you can see, being an isentropic expansion, you can have a vertical diagram, vertical line over here on a TS diagram. So, one has to locate this point on a TS diagram. When there is isentropic expansion, what you have to do is to draw a vertical line from point 3 and see where it intersects on the low pressure return line, and that is a point where the point E would lie, because this is a completely 100% isentropic expansion. So, the gas expands from point 3 and joins the return stream at point E, where it gets mixed up with the return stream, where it joins the return stream. Okay, coming to the high pressure line again, at point 3, the gas which is going to be here at this point is M minus Me, because Me has been diverted through the expansion engine. So, what is going ahead from after the point 3 is M minus Me. This gas further getting pre-cooled from 3 to 4, and this is what you can see on the TS diagram. It gets pre-cooled from 3 to 4, and this 4 would match the outlet temperature of this heat exchanger, which is 7. All right. Being a 100% heat exchanger effectiveness, we can see that this point matches over here. Now, this gas will be getting further pre-cooled from 4 to 5. This gas amounting to M minus Me is getting further pre-cooled from 4 to 5 by the return stream, which is going after liquefaction. So, what is the return stream will have? The M minus Me is the gas which is getting expanded from 5 to 6. It will fall in a dome, and corresponding to length of the 6 to G, you will get liquefaction, okay, depending on the point where it falls. Here the M dot F is collected from the container, and the return stream would therefore have M minus Me minus Mf. Okay. So, out of the gas which is M is compressed, Me is going to be expanded through the expansion engine, and it joins here at point E. What is going to come ahead beyond this point is M minus Me, out of which M dot F is collected. So, what is remaining and what is going back in the return stream is M minus Mf minus Me. This is very important because we have to understand about this in subsequent slides. Okay, so, the gas which is going back is M minus Mf minus Me, which is at point G, which is a gas over here. At this point, the gas comes out at 7. So, you can see from here it comes to 7, which is a warmer, which is on a higher temperature side, because it matches with the temperature 4. However, the cold gas which is expanded from 3 to E comes at a much lower temperature, as you can see. It will depend on what is the point number 3, where the point number 3 is. Okay, in a TS diagram, where the point 3 is, depending on that, the point E would be decided, and this stream which is coming at point 7 will combine with the temperature with the Me flow rate and coming out at temperature at point E. So, as a result of which, as you can see, the heat exchanger output is actually at T7, while the expansion engine output as TE. Combining both these, the point at the entry of this second heat exchanger is coming at point 8. This is because of the cold which is going to be generated from during the expansion 3 to E. I hope this is clear. Depending on the expansion point E and depending on the point 7 which comes out of this heat exchanger, these two streams will get combined, and they will be getting combined by enthalpy rule. That means, they have to be multiplied by their respective flow rates, that is M minus Mf minus Me into H7 plus Me into T, H enthalpy at this point E, which would result in a some enthalpy which will corresponding to point number 8, the temperature corresponding to point number 8. Now, the gas enters at point 8 and it would come out at point 9, and this now gas will be M minus Mf over here, because Me has joined the return stream. The stream going to the second heat exchanger now will have M minus Mf as the mass flow rate. So, this gas entering at 8 will get warmed up to point 9, which matches with point 3, and further this gas point 9 enters through after the first heat exchanger comes to point 1, where the makeup gas would join amounting to M dot F, and the cycle continues. I hope this TS diagram, which is a very important diagram to understand, has been understood by you. What is important to understand is what is that Me has been drawn from the main circuit, at what T3 temperature it has been drawn off, and how much amount of M dot F or what is your return stream gas is left. What you can see is all these heat exchangers are basically having different flow rates. For example, in this heat exchanger you got a M dot flow rate over here, while its the return stream has M minus Mf. This has M minus Mf and this has M minus Me, well this has M minus Mf, and the third heat exchanger will have M minus Me over here, while it will have M minus Mf minus Me over here. Okay, so these heat exchanger are kind of imbalanced heat exchanger, means that the flow rates in both the directions, the hot stream and the cold stream flow rates are different. Okay, if you have understood this diagram, we can go ahead now in order to compute the expression for the yield. So, if we take this as a working volume, so consider a control volume as shown in the figure, and applying first law, what we have is this we have done plenty number of times earlier for various cycles. So, I will not go into details of these calculations, but I will just show you the final expression which comes out in 1 or 2 steps. So, what is going in has to come out, that is what your first law says. So, what is entering at this point is m dot H2, and what is coming out of this control volume is m dot E. So, m dot H2 is equal to W E plus the return stream which is come at this point, which is m minus mf into H1 plus mf HF, which is going to come at this point. All right. The expander work output, that is W E, is given by what is entering the expansion engine is ME into H3, while what is leaving is ME into HE. So, WE is equal to ME H3 minus ME HE. Okay. So, basically the flow rates are same, it depends on the enthalpy difference between H3 minus HE or T3 minus TE on a TS diagram. So, if you put this value of ME over here, what you get is m dot H2 into m minus mf H1 plus mf HF plus ME H3 minus ME HE. Okay. By reorganizing this or rearranging this, what we get ultimately is this y, which is nothing but m dot f upon m dot is equal to H1 minus H2 upon H1 minus HF, which is what we are familiar with this expression now, plus x time H3 minus HE upon H1 minus HF. And what is x? X is nothing but the mass flow fraction of the stream which gets expanded. So, ME m dot E divided by m dot. So, depending on how much m dot T, how much mass fraction of the total mass flow rate has been taken off for expansion, this value of x will be determined. So, basically the amount of gas which goes through this, if the more gas goes through it, more and more cold will get generated. However, if you take lot of gas from here, as you can understand, less gas is going to in front. Okay. So, m minus ME which is going front is basically some gas out of that stream is going to get liquefied. One has to be very careful about how much gas is taken and at what temperature is taken, and this is what we are going to see in subsequent slides. So, where the expander mass flow rate is denoted by x over here. So, what you can see is H1 minus H2 upon H1 minus HF is a very familiar expression for you, and the Claude cycle brings this additional component or the next bracket, because of which y gets increased. So, the first term is the yield of a simple Linde-Hampson cycle, which we have seen that it depends only on the point 1 and 2, the compression process 1 and 2. The second term, which is an addition to the simple Linde-Hampson cycle, is basically coming because of the expansion engine over here. So, second term is a change in the yield occurring due to the expansion engine in the cycle. For a given initial and final conditions of P, that means if the point 1 and 2 are fixed, the yield y depends on H3. So, if you see this expression, the y value depends on 1 and 2 and 3, because as soon as your 3 is decided, the point E is also decided immediately. So, 3 will be decided on the enthalpy 3 will depend on what is the corresponding temperature at which the expansion starts. All right. So, y would depend, if your 1 and 2 points, that means the pressures are fixed, it will depend on the value of x and the temperature T3 from where the expansion takes place. All right. And if we say that if the T3 also is held constant, then the yield depends on only x. So, this is constant if your point 1 and 2 are fixed, and on your pressure number 2, on your pH value, your temperature is also fixed, because of which your H3 minus HE also gets fixed. This becomes a linear function of x now, because this is a constant, this also becomes a constant, and the value of x, however, could be variable. So, in this case y will be a linear function of x when the temperature T3 is fixed. But for a case is equal to x is equal to 1, now can I do this? Can I fix the value of x? I can go on increasing the value of x, I am sure I will get y increased. So, I can theoretically I can go on increasing the value of x, but take a limiting case that if I make x is equal to 1, that means whatever gas is coming from here is expanded. That means no gas is going to go in front. In that case, y should be equal to 0, and if you look at this expression, I will not get the value of, when x is equal to 1, I will not get the value of y to be equal to 0. Why? Because that particular case has not been taken into account over here in this expression. All right. So, for x is equal to 1, what happens when x is equal to 1? The gas in the return stream, which is m minus mf minus me, is equal to 0 actually. Actually, the gas which comes over here also equal to 0 basically. So, if we want that the heat exchanger has to function, that means there should be return stream. you got a onward stream and you should have a return stream also, and in order that return stream is finite value, your m minus mf minus me should not be equal to 0, right. So, it means that in order to have a finite yield, that means in order to have a finite value of y at this point, your m minus mf minus me, which is nothing but the return stream at point G, has to be always more than 0. That means, it should be some finite value, so that the heat exchangers function. So, if we divide the whole thing by m, what we get is 1 minus y minus x, which is more than 0, and if I rearrange that, what I should get is x plus y should always be less than 1. It means that in order that heat exchangers function, in order that I should get some finite return stream, I should see to it that x plus y is always less than 1. If your x plus y is less than 1, all these things is possible, and this expression of y is equal to this bracket plus x times this bracket is valid only when your x plus y is less than 1. When x plus y is equal to 1, that means there is no return stream basically. X plus y is this thing, whatever x has been directed and remaining y is equal to 1, then I will not get any return stream at this point. So, one should ensure that x plus y is less than 1, always less than 1. However, from this expression I can go on increasing the value of x and I can get y also has increased value. So, it has no meaning. So, therefore, as soon as this particular expression start giving x plus y as more than 1, we should not use this expression. This expression is valid for x plus y less than 1 only. Therefore, the above equation is valid only when x plus y is less than 1. The yield y of the system increases with the increase in the value of x for a constant value of T3. That is what we have seen, that if we start increase the value of x from let us say 0.1 at a particular value of T3, it will start increasing with the value of x in a linear fashion. Based on y calculated from the above expression, when the sum is x plus y becomes more than 1, that is what I just talked about. When utilizing this equation, when we reach a condition that x plus y is more than 1, we know that a limiting value of y must be calculated now, and what we say, as we say that x plus y has to be less than 1, let us compute a limiting value, that is x plus y is equal to 0.99. Okay. In that case, I will calculate my y. When my x plus y happens to be more than 1, in this case, I will calculate the y is equal to 0.99 minus x. This could be 0.999 also minus x, but I am taking only 2 digits. So, y is equal to 0.99 minus x when we reach a condition that x plus y is more than 1. In summary, how do I calculate y? Y is calculated using the above equation until x plus y is less than 1 or 0.99. So, this expression is valid when x plus y is equal to 0.99, after which a limiting value of y can be calculated by y is equal to 0.99 minus x, and this is what a general principle we are going to follow to calculate the yield using Claude cycle. I hope this is clear to you. This value is the maximum y value because I am taking 0.99. Okay? This is the maximum y value that is possible, but the actual value could be less than this value. Okay, the actual value could be less than this value, but this is a limiting value. That means, the y can't exceed this value in any case. It is clear that the work interaction of the system with the surrounding is due to. Now, let us calculate the work requirement for this system, and where the work comes into picture is compressor and expander. Compressor, we do the work on the system, and expander, we get a work output, that means work is done by the system. So, the net work requirement, if the expander work is used in compression process, ideally whatever work is done by the system, it could be transferred to the compressor basically, so that it decreases the net work which has to be done by on the compressor. So, minus W net is equal to minus WC minus WE. The negative minus WC is the work done on the system. So, work done on the system is negative and work done by the system is positive. So, it is a net difference between what is done done on the system minus work done by the system. As we have stated earlier, using the control volume first and second law for compressor, this is a very standard equation which we have used almost in all the cycles, that work done on the compression is equal to m dot into T1 into delta S across 1 and 2 minus delta H across 1 and 2. It's a very standard equation which has been used. Similarly, the control volume for expansion engine also gives us what is entering is ME at point 3, and what is leaving is ME at point E at this point, and also what we are getting at output as output is WE. meaning which WE is equal to ME into H3 minus HE. We have talked about this earlier also. So, if I put them together, I will get dividing by m dot to the expression, I get W net upon m dot, that means net work done per unit mass of gas which is compressed is equal to T1 into S1 minus H2 minus H1 minus H2 minus X into H3 minus HE, where X is equal to m dot E upon m dot. So, basically the first term again X is the expansion engine flow rate. So, what do you understand from this? That this is the work done on the compressor. The first term is the work requirement for simple Linde-Hampson cycle, where the only compressor comes into picture, while the second work is the work done by the system, and it is coming only because the expansion engine is in place in the cycle now. All right. So, this is the work done by the system amounting to WE. The second term is the reduction in the work requirement occurring due to the modification. But you may understand that the work output what you get at this point, which is expansion engine, is much smaller as compared to work done on the system. Okay. So, if we are talking about kilowatts over here, what you get here could be 50-60 watts only over here. However, that is also we have considered that sometimes we may consider, sometimes we do not consider also, but theoretically we can consider that whatever net is available is work done on the system compressor minus work you get from the expansion engine, although it could be possible that this work output you get from the expansion engine is very, very small as compared to the work done on the compressor. Based on what we have learned in the Claude cycle, it will be very useful. Now, we take a small tutorial and we do the parametric studies using this tutorial, where we can understand the effect of values of the gas X, the concept X, or the gas amounting to m dot E, which is diverted to the expansion engine. And also we will try to worry about what happens if the temperature T3 from where the expansion happens, what is the role of T3 in these calculations. Okay. So, from that point of view, this tutorial has been framed. It reads as, it has got a part A and part B. The part A is determine W by MF, that is work of compression per mass of gas liquefied for a Claude cycle with nitrogen as a working fluid. So, one can have air, oxygen, nitrogen, etc. with nitrogen as a working fluid in this case. The system operates between 1 atmosphere and 40 atmosphere, or 1.013 bar and 40.52 bar. The expander inlet T3 value is 225 Kelvin, that means it is below ambient. The expander flow ratio is varied between 0.1 and 0.9. That means you can see the value of X is varied between 0.1 to 0.9, and what we want to see is what is the effect of this variation of X on the value of W by MF. Now, in this problem, what we have done, the value of T3 has been fixed at 225 Kelvin. In the part B, we want to study, repeat the above calculations for T3 is equal to 300 K, 275 K, 250 K and 225 K. So, herein we can see that what is the role of this T3 in the entire cycle. If we reduce the value from 300, 275, 250, 225, etc., how does it change the value of Y and W by MF? So, what the problem says is plot the data, that is Y and W by MF versus X graphically and comment on the results. So, basically here we want to study the effect of the value of T3 and the value of X, which is varied from 300 point to 25 K and 0.1 to 0.9 Kelvin respectively. And we want to study how do these parameters affect Y and W by MF versus X. When we graphically plot, we can, the nature would be clear. So, as we go in the every circuits, every cycle, we see that what is the problem? The problem is we got a Claude cycle, we got a Claude system. The working pressure is 1 atmosphere to 40 atmosphere here. The working fluid is nitrogen. The value of T3 variations what we want in total is from 300 Kelvin to 225 Kelvin. So, 300, 275, 250 and 225, that is in steps of 25 Kelvin. The mass flow fraction, that is X, is varied from 0.1 to 0.9. As I said earlier, X cannot be equal to 1. That means, all the gas which comes cannot be diverted through the expansion engine. All right. So, it has to be less than 1. For the above system, what is asked from you is to calculate the work per unit mass of gas liquefied, and for which you have to do the calculations of Y. One has to calculate Y first, and this W by M divided by Y will give you W by MF. And this study is, as you can see, is we are going to have 1, 2, 3 and 4 for 0.3 at 300, 275, 250 and 225 Kelvin, and this is what the overall problem is. So, in the part A, the expander inlet condition under study is 225 Kelvin and at 40.52 bar. The expander mass flow ratio varies between 0.1 and 0.9. What we are going to do now? I am not going to solve all the problems for all the values of x from 0.1 to 0.9. What we are going to do in detail is to understand in this tutorial how Y and WMF are calculated for x is equal to 0.2 for example, and T3 is equal to 225 Kelvin for example as an inlet condition. What we expect you to do is now complete a table. We will give you a complete table, and what we expect you that you will solve it out yourself, so that you can see that you have understood the problem. So, now let us see the Claude cycle, and here is the Claude cycle having a compressor and expansion engine. And what we have is a 0.1, 2, 3, 4, E and F. So, one can see that 0.1 is over here. Let us try to locate the points. 0.1 is at 1 bar, 300 Kelvin, corresponding enthalpy entropies are given at 0.1. 0.2 is the after the compression, and again at this 0.2 we got the pressure temperature conditions given over here with the corresponding enthalpy entropy values. The 0.3 happens to be what is given in the problem, which is what we have taken as 225 Kelvin, and the pressure is same as what it is at 0.2. Corresponding enthalpy entropy are again calculated out here. As soon as the 0.3 is fixed on a TS diagram at 40 and 225 Kelvin, we get the point E, which is over here, and the temperature at this point E happens to be 80 Kelvin. So, what we do basically, we have got a TS diagram, we draw a vertical from 225 Kelvin on 40 bar line vertically down, where it intersects the temperature on 1 bar isobaric line, and wherever it intersects the corresponding temperature happens to be 80 Kelvin. So, the point E is located on P is equal to 1 bar isobar line by drawing a vertical line from 0.3, and this has to be graphically or from a TS diagram it has to be taken. Okay. And the pressure at this point is going to be low pressure line, because this is a return stream. The point F happens to be the boiling point of nitrogen, which is 77 Kelvin. So, here F is where from you collect the liquid, from where you get the yield value. Okay. So, different properties in terms of entropy and enthalpy, this is the most important part. If you commit any mistake on this, then the whole problem is going to go wrong. So, one always should have the habit of locating this point 1, 2, 3, E and F, and correspondingly one should correctly write the value of enthalpy and entropy. This is a very common mistake students commit, because they read the TS diagram very fast, the correct points are not located, and sometimes what you get is your yield also happens to be negative and things like that. So, the enthalpy entropy value have to be correctly taken from the TS diagram. One can see the corresponding TS diagram here. 1, 2 is a compression, 2 to 3 is a cooling, 3 to E is where you get the point E, that is what I just said, that we draw a vertical from high pressure line at 0.3 to the low pressure line, which intersect this point at E, and corresponding to this what you get is 80 Kelvin in this step, in this particular case. The temperature at 0.3 is 225 Kelvin. So, the expander inlet condition and its mass flow rate are 225 Kelvin, and how much gas is going in this particular problem is we are saying x is equal to 0.2. So, 0.2 times m dot is the gas which is sent through this expansion engine. Okay. So, fraction which is going through the expansion engine is only 0.2. That means, what is coming out at this point is 0.8 fraction of the total mass flow rate over here. So, let us start doing simple calculations and calculate the liquid yield by the formula y is equal to H1 minus H2 upon H1 minus HF plus x time H3 minus He upon H1 minus HF, where x is equal to 0.2 in this case, T3 is equal to 225 Kelvin and 40 atmosphere pressure. So, taking the respective points from this table, from where enthalpy entropy have to be read, let us calculate the value of y is equal to H1 minus H2, which is 462 minus 453 upon H1 minus HF 462 minus 29. plus x time, that is 0.2 times H3 minus He, which is nothing but the difference between these two values, divided by H1 minus Hf, and this will give you 0.086. So, y, that is m dot f upon m dot, is only 0.086. Okay. So, this much fraction of gas gets liquefied when 0.2 fraction is diverted through the expansion engine, and this is what we have calculated. Now, let us calculate even W by mf by the same technique. So, if I want to calculate work per unit mass of gas compressed, the formula is Wc by m dot, which is nothing but T1 into S1 minus S2 minus H1 minus H2 minus x times H3 minus He. Again, taking the different entropy values and enthalpy values as given over here, this is the calculation you do, and what you get at the end is 299 joule per grams. So, this is the net work done on the system, sorry, this is the work done on the compressor, not net work done, but this is the work done on the compressor, and work done per unit mass of gas liquefied is Wc by m dot is equal to 299, y is equal to 0.86, and Wc by m dot f is 299 upon 0.086, which is 3476.7 joule per gram. All right. So, what you get from here is the work done on compression per unit mass of gas which is liquefied. We have not taken the value of We over here. Okay. We have not taken the value because that value happens to be a very small quantity. Extending this calculation for all the values of x and tabulating the result. So, what we have done, I have just calculated the value of y and W by mf for x is equal to 0.2, for the value of T3 to be when it is equal to 225 Kelvin. Now, what I will do, I will give a sweep to the value of x from 0.1 to 0.9. Remember all the discussion what we had earlier regarding where do we use this expression, and after a limiting value what expression do we use to calculate the value of y. So, extending this completely, and I am not showing all the details, what I show is a table which gives when T3 is equal to 225 Kelvin, when you vary the value of x from 0.1 to 0.9, the corresponding y values are given over here and corresponding W by mf values are also given over here. So, what you can see here, as we had seen that as the value of x1 is increasing, as the value of x is increasing, y increases linearly up to the point when x plus y is limiting value. In this case, what we have done, it has to be less than 1, or in this case it is 0.99. Okay. So, you can see that when the x is increased from 0.1 to 0.73, at x is equal to 0.73, y goes on increasing and meets a limiting value of 0.26, where after that if x goes on increasing, I cannot use the earlier expression because x plus y happens to be more than 1. In that case, we have used the limiting value of y, which is 0.99. We have used the limiting value of x plus y is equal to 0.99, and therefore, y has been calculated as 0.99 minus x. So, you can see the sum here happens to be 0.99 all the time. This is the limiting value of y, that means actual y could be less than this y, but definitely not more than this. Having calculated y in this fashion, we have calculated W by mf also, and that also uses this y values, and what you can see is the results over here. What does the result show you? The result show you that as the x increases, the y value increases and goes through a maximum of 0.26, and after that it makes a limiting value and it starts coming down. So, the value has started coming down, it has reached maximum. Similarly, what you can see on W by mf, that as the value of x increases, the W by mf value or the work done per unit mass of gas liquefied decreases, and that is basically where the principle of using expansion engine happens. That expansion engine, the amount of gas which is transferred or which goes to expansion engine should be such that the W by mf has to be minimum and y has to be maximum for that particular temperature T3. Okay. So, W by mf goes on getting, the value goes on reducing and it meets a minimum value at which y happens to be maximum, because W by mf is nothing but W by m upon y. So, wherever y get minimized, the value of W by mf will be maximum over there. Okay, so the value of W by mf reaches the minimum value over and again it starts increasing. So, this y goes through a maximum and W by mf goes through a minimum, that is what we understand from this. So, if I plot these things, that is y versus x, what we have just calculated, and I just take 4 representative values or 5 representative values over here, and if we calculate case number 1, 2, 3, 4 and 5, and what if I join, what you say is this is a x, when the x is varied from 0.1 to 0.9, y goes through a maxima and the maximum value happens to be around 0.25 or 0.26 for T3 is equal to 225 Kelvin temperature. If I do this from the plot, it is clear that y crosses a maxima when the value of x is increased from 0.1 to 0.9 and the optimum value of x at which the y is maximum happens to be around 0.73. Beyond this maxima, with up to this point we had used the expression which was given as y is equal to h1 minus h2 etc., what we have calculated earlier. Beyond this value, what we have used y is equal to 0.99 minus x, it is a limiting case of y over here. Okay. Similarly, if I compute the value of W by mf versus x, I see that the value of W by mf, as I said earlier, it starts coming down, it hits the minimum value and then it starts going up. And if you plot this 1, 2, 3, 4, 5 cases over here, what you see is for T3 is equal to 225 Kelvin, I get minimum at this point again around 0.73 and this condition is for T3 is equal to 225 Kelvin temperature. The trend shows that the W by mf crosses a minimum with an increasing value of x. Beyond this minima, the W by mf is estimated based on the limiting value of y, this is clear. Now, all the calculations are pertaining to the part B, which is what we have done till now is part A, and in part B now what we are going to change is the value of T3 and we will give a sweep to the value of T3 also. That means, we will go for T3 is equal to 300, 275, 250, 225 etc. and for every value of T3, we will have a sweep of even x value from 0.1 to 0.9. It means there is a lot of calculations involved and what we have done is written a small program and from where I will now show the table the results. The results are calculated and shown here. So, what you can see now here is the value of T3 is equal to 300 Kelvin, 275 Kelvin, 250 Kelvin. I have already done the value calculation for 225 as T3 value. So, this is the value of for T3 is equal to 300 Kelvin. This is actually room temperature basically, the expansion happens at room temperature only. If you see from here, I am going to shift from 0.1 to 0.9 and correspondingly the value of y are calculated. And here you can see that the maximum value of y happens to be for x is equal to 0.67 and the maximum value of y is 0.32. If I reduce the value of T3 to 275 Kelvin, the maximum value of y happens to be 0.3, which is little less than this, and the corresponding x happens to be 0.69, that means little higher than this. If I come further down from here, T3 is equal to 250 Kelvin, the maximum value of y is 0.27, which is less than this, and the corresponding x value is now 0.72. Okay. And if you remember the 225 Kelvin, it was 0.73 and around 0.26 for T3 is equal to 225 Kelvin. That means, as you go on reducing the temperature over here, the y value goes on optimum y value or the maximum y value goes on decreasing and correspondingly the amount of gas which can get transferred to the expansion engine has shown an increase over here 0.67, 0.69, 0.72 and 0.73 for expansion engine when T3 is equal to 225 Kelvin. However, please understand that all these calculations have been done for heat exchanger effectiveness 100% and expander efficiency is 100%. As soon as the inefficiency parameter starts coming in, these values can change, all right, the optimum can shift accordingly. So, all the calculations pertaining to part B are again shown for W by mf here. So, again the same thing is done for T3 is equal to 300 Kelvin, 275 Kelvin, 250 Kelvin, and again what you see is a minimum is at 0.67, 0.69, 0.72, while W by mf shows an increased value when the T3 value is decreased. This is very difficult to follow a table. If I plot this graphically, it will make more sense and therefore, all these calculations are shown graphically where some conclusions can be directly drawn. So, if I draw this liquid yield y versus x, what you can see is y versus x for different T3 values and this is for 225 Kelvin The second curve is for T is equal to 250 Kelvin. The third curve is for 275 Kelvin now, and the 4 Kelvin what you can see is for 300 Kelvin. So, what you can see from here is as the value of T3 is increased, that means 225 to 275 to 300 Kelvin, my Y or the yield has increased. Okay. So, theoretically I can understand that I can carry out the expansion from as high temperature as possible, which is 300 Kelvin in this is going to be beneficial. As mentioned earlier, Y crosses a maxima with increase in the value of X for each T3. So, every T3 what you see, it has gone through a maximum, and what you can see from here, the position of this maxima shifts to the right when decrease in temperature value of T3. That means, if I come down from 300 to 225 Kelvin, the optimum X value has changed. It is a marginal change, however, from 0.67 to 0.73 or so. That means, but because the temperature has decreased down, that means when the temperature decreases down, I can send more gas through the expansion engine. I can divert more gas through the expansion engine to get an optimum. The optimum requires more gas to be diverted through the expansion engine. Why? This occurs because the expander work H3 minus He decreases with the decrease in temperature T3. So, I go down the temperature from in this dimension. What you can see is the Y in the formula is a function of X into H3 minus He. If you remember the formula, Y is equal to H1 minus H2 upon H1 minus Hf plus X time H3 minus He upon H1 minus Hf. So, the product of X into H3 minus He I would like to get maximized because I want to see the optimum associated with those values. So, as soon as I go on lowering the temperature, the value of H3 minus He is going to get less and less depending on a TS diagram for a particular gas. So, because H3 minus He gets reduced, I can divert more and more gas so that I get a optimum value, alright, and that is the reason that I can divert more and more gas when I come down lower in temperature. Also, at the lower values of T3, more amount of gas can be diverted to the expansion engine. That is what I just talked about. This is because the product X into H3 minus He is to be maximized. I hope I am clear on this. However, the T3 is limited by the position of the point E. One can't really come down below a particular temperature because the isentropic expansion from that point 3 might fall in the dome, which is undesirable because the expansion engine would not like to see the liquid in the expansion engine. It wants to be in gaseous stage, and therefore, how much to be lowered, the temperature, how much T3, how much it has to be lowered is limited by the value of isentropic expansion from point T3. If I do the similar thing now to understand the W by mf versus X, this is a curve for T is equal to 225 Kelvin, and if I draw for 250 Kelvin followed by 275 Kelvin and followed by 300 Kelvin. Exactly in the similar line what I talked about, at 300 Kelvin, because I get maximum Y value there, I get minimum W by mf over here. While if I lower the temperature, my W by mf requirement increases. As stated earlier, the W by mf crosses a minima with the increase in the value of X for each of the T3 values. Also, the position of this minima shifts to the right. So, my optimum value shifts to the right with the decrease in the value of T3. So, as I decrease the value of T3, the optimum value shifts to the right because my optimum Y happens to be for those respective X values. This can be well understood from what we have studied for the Y values. Y versus X behavior is absolutely similar to what we are seeing in this particular case. The minima shift to the right because expander work H3 minus He decreases with the decrease in the value of T3. Also, at the lower values of T3, more amount of the gas can be diverted so that the product X into H3 minus He is maximized. This is what we talked about earlier for the Y versus X case. And this is what has to be well understood, that why it goes to a minimum and why it shifts to right in this particular case. With this, if I summarize whatever we have learned today, the JT expansion is an irreversible isenthalpic expansion, and an expansion by an expansion engine is an reversible isentropic process. This is clear. In a Claude system, the energy content of the gas is removed by allowing it to undergo an isentropic expansion. alright. So, the energy is basically because of the work done by the system due to the isentropic expansion. The yield and the work requirement of the systems are Y is equal to this formula, which I am sure now you are conversant with, and W net by m dot is equal to this formula, of which this is the work done on the compressor, this is work done by the expansion engine. If T1, T2 and T3 of the system are held constant, the yield Y of the system is a linear function of the expander mass flow ratio x. Again, this is clear from the yield expression for Y. The equation for Y is valid only when x plus y is less than 1. Beyond a certain value of x, a limiting value of y is estimated as y is less than 1 minus x. I am sure this is clear. Why are we doing this? Because we want the return stream to be having a finite mass flow rate. It means m minus me minus mf has to be more than 0. For a given temperature of T3, the yield y crosses a maxima with an increase in the value of x. So, if we give a sweep to x, the value of y goes through a maximum, and this is what the value of y we want to attain. Also, the maximum shift to the right with the decrease in the value of T3. We have talked about this. For a given value of T3, the W by mf of the system goes through a minima with the increase in the value of x, and this is again the optimum value of x we would like to attain or use for design purpose for cycle optimization. Also, the position of this minima shifts to the left with the decrease in the value of T3. All right. With this background and with this tutorial, an assignment is given to you on the similar line. Nitrogen as the working fluid, but we have changed the pressure to 50 atmosphere, and again the T3 has to be at 250 Kelvin, expander flow rate to be varied from 0.1 to 0.9. And again I would like you to repeat the cases for temperature, because what happens to the optimum, we have done a case for 40 bar or 40 atmosphere pressure. As soon as you go to 50 bar, what happens to optimum x value, what happens to optimum y value, and what happens to the optimum W by mf value has to be well understood. All right. So, these are the answers for your questions, and I am sure you will take care of y versus x and try to tally your answers. Similarly, W by mf upon x variation also has been given for different T3 values. Please carry out this exercise and try to see that your results are matching with these results. Thank you very much.